Okay, vector geometry, the last chapter in our textbook and in our course. So pause and copy. Let's have a look at this example. So I'm trying to find a certain vector, the vector AB. So what I mean, it's the vector that you can think of it as connecting A and B. Like this. So you can think of that as being AB. Okay, now I'm going to calculate that using the vector that goes from the origin to A. So this vector. And I'll also use the vector that goes from the origin to B. Try to draw this straight. So I would call this 0B. I would call this vector down here 0A. Now, if I look at that diagram, I can see that taking this vector, adding this vector, gives me this vector. Think of it that way. 0A plus 0B is equal to, 0A plus AB gives me 0B. So AB is 0B minus 0A. Okay, so this is the formula you should either memorize or be able to produce on command. So in our case, we have AB, 0B. Well, here's the point B. The vector I would write vertically like that, then subtract 0A, which is 1, 2, giving you 2, 2. Okay, so looking down here, I'm distinguishing between the point B, which I would write, well, at least in this chapter. In chapter 5, I'm going to distinguish between the point B and the vector 0B. Now, I think we should move on. Okay, exercise, pause, copy, try. Pause, copy, try. So this one's a bit different. You want to take this equation and solve it for what you want. What you want is 0B, right? 0B is AB plus 0A, which is 1, 1 plus 2, 3, which is 3, 4. Therefore, B is equal to, is a point 3, 4. Okay, let's define, just focus here for now. Definition of magnitude. We're going to call this the magnitude of a vector or the length of a vector. So what we're doing here, if I may draw a little picture up here, you have a vector x, and you have x2 here. Let's say it's right there. And you got x1 here. And then the length of x is this side length. Okay, if you imagine this to be a triangle here, Whoa, not good. If you imagine this to be a triangle, a right angle triangle, you can use Pythagoras to get this formula. So that's our definition. That's what we will define to be the length of a vector. Okay, if you have higher dimensional vectors, you just extend this to however many components you have. When you get to 4-dimensional, you can't see this anymore, but in 3 dimensions, you can verify that this length is indeed what you want it to be. Okay, this quantity here will be the length of the vector in the way you probably already think about it. Okay, I want you to try this exercise now. Okay. So to find the length, we just square the components and add them up. What do you get? You get square root of 53. My answer is 3 root 6. What have I done wrong here? I've said the answer is 3 root 6. What did I do wrong? Did I copy it down wrong? I don't know. 4 plus 49 is 53. 53 is a prime number. 1, 2, 3, 4, 5, 6, 7, 3. Yeah, prime number. Okay, ignore this answer. Who cares? Moving on. Okay, we have a theorem here that allows us to factor out constant multiples. Okay, because we're doing length, and lengths are positive if they want to be meaningful, we need an absolute value here. Now, for this example, I'm telling myself to repeat the preceding exercise. Let's not do that. Let's do something different. How about we do 27, 9, 18. What is the length of this? Well, the length is going to be 27 squared plus 9 squared plus 18 squared. But that is not a very efficient way to go about this problem. What I should do is that I should factor out the 9, common factor 9 here, here, and here. So that's 9 times 3, 1, 2. So the 9 can come out. 9 times 3, 1, 2. This is much easier. 9. Now I do my formula. I get 9 plus 1 plus 4, which is 9 square root 14. So we get a nice reduced answer at the end here.